In this video, we are actually going to find a potential function, knowing that we are given a conservative vector field. In the video before this, we were given this vector field and we showed using partial derivatives that it was a conservative function. And what we know is that if a function is conservative, then there's a potential function such that the gradient of the potential function is equal to that vector field. Now we have two methods that we can kind of use, or two different ways that we can think about how to do this. What we want to think about is recall that this right here, 2x y cubed, represents the partial of little f with respect to x, and then this second component function, 1 plus 3x squared plus y squared, represents the partial of little f with respect to y. So of my two methods, I'm going to start with one or the other, and we just need to make sure that we're paying attention to integrating with respect to the correct variable. Main thing we want to remember is that the gradient of little f represents that vector force field. So I'm going to start with one of these two partials. So let's think about this. What I know is that my multivariable function, little f, is going to equal the integral of partial f, partial x, dx. Or rather, 2xy cubed dx. So when I integrate this, I've got to keep in mind, since this is a partial of the function with respect to x, that there could have been some constant. And that constant, remember, if we were integrating with respect to x, we would treat y as a constant. So that constant could have been a variable y. So when we integrate and we get that constant, we're going to actually have to solve and determine what that constant could be as a function of y. All right, so what we have here is that f, and when I integrate this, we leave y as a constant, and so that will become 2x squared over 2, or just that f equals x squared y cubed. And generally we write plus c. But again, this c could have been some expression with a y in it. So I'm actually going to write k of y here. So this represents a constant, but it could be a constant in terms of y. So at this point, now I'm going to take this and differentiate with respect to y. So I'm going to take that partial of the function with respect to y, and that gives me 3x squared y squared plus, that would become k prime of y. So now I've differentiated partially with respect to y. So what I'm going to do is I'm going to use this partial f with respect to y, and I know what partial f is with respect to y is equal to. It's equal to 1 plus 3x squared plus y squared. So I'm going to take that, plug that in down here, and now I can use that to figure out what this constant function could have been. So on the left, I have 1 plus 3x squared y squared equals 3x squared y squared plus k prime of y. Very easy for us to see here that k prime of y is going to equal 1. So once I've done that, now at this point, I'm going to take this and integrate with respect to y. So the integral of k prime of y, that's the integral of the value we just found, 1, and we're going to integrate with respect to y, which gives me y plus c. And we've already taken care of x, so that means c is just a constant. We already dealt with x up above. So now we know what k of y is equal to. This guy right here is equal to k of y. So this can plug in right up there. And we will say that my function in terms of x and y is equal to x squared y cubed plus y plus z. And what we have here represents our potential function. We can verify that this is the correct potential function by finding the gradient, which would be taking the partial of this with respect to x, and then the partial of this with respect to y, ensuring that we get these two terms or component functions of my vector field that I initially started with. So I said there were two methods. I started with the partial of f with respect to x and solved, or we could start with the partial of y, and really it's just a matter of opinion. So in this video, we started with a vector field, which we knew was conservative, and then we determined what that potential function was such that the gradient of the potential function equals the conservative vector field. We kind of had to solve a system of equations in a sense because we were dealing with two variables. So now in this situation, we only had a function of x and y. Three variables, it gets kicked up a notch. So let's look at an example of that. So let's look at finding the potential function again. Here we have a function that's going to be three variables because we have x, y, and z here. So we know the field is conservative, and if it is conservative, that means we can find a potential function. So I'm going to go ahead and start. I'm going to label my partials. Partial f with respect to x is y plus z. Partial f with respect to y is x plus z. And partial f with respect to z is x plus y. So what we're going to do is we're going to start the same way. In this case, we have three starting points. I'm just going to start with partial f with respect to x. And what we know is that my function of x, y, z is going to equal the integral of df dx integrated with respect to x. So that's the same as the integral of y plus z integrated with respect to x. Integrating that, we're going to get xy plus xz plus a constant. Now, in this case, because we've only dealt with x, this constant is actually a function of the two missing variables. So since I only integrated with respect to x, I'm going to write this a function g, and those variables are going to be y and z. So we know that this is what f is equal to. At this point, we're going to repeat that process that we did in the last example, and I'm going to take the partial with respect to y. So partial f with respect to y. What does that give? For this term, I get x. For this term, I get 0. And for my function here, I've got partial of g, y, z with respect to y. Or rather, just to simplify our notation, I'll say partial of g with respect to y. Here now, I know what partial of f with respect to y is. It's going to give me x plus z. So the partial f with respect to y, that's x plus z. I still have that x plus partial g respect to y. You'll see that the x's will cancel here, and you get that the partial of g with respect to y is equal to z. And this should make sense because if I plug z in for this term right here, x plus z. X plus z is equal to partial f with respect to y. So we've got partial of g with respect to y. I know that if I integrate with respect to y, that's going to give me my g function, which I need to plug in to my regular potential function. So g of y z equals the integral of partial g with respect to y integrated with respect to y, or rather the integral of z integrated with respect to y, which gives me zy plus a constant. So again, this constant, we have not dealt yet with that z variable. So this is still a function. So I'm not going to write c plus c like I normally would. I'm going to write plus h of z. So now we are going to come back up here and look at f. We've got f. We solved for g right here. So I'm going to plug that in. I'm going to rewrite my function f of x, y, z. I'm just going to write f equals xy plus xz plus this function I just found, zy plus h of z. So now I've worked through this. I integrated with respect to x. I took a partial with respect to y. I integrated with respect to y. What do you think we need to do next? Now we're going to take this and differentiate with respect to z. So we can deal with z, and then we'll have one more integrating with respect to z step. So I'm going to take this guy right here that we're dealing with. I'm going to take the partial with respect to z. So I now have df dz equals, well, there's no z here, so that's a 0. Integrating this term here, x is a coefficient, so I have x. Integrating this next term, y is a coefficient, so I've got y plus h prime of z, or rather partial h, partial z. Okay, so here's where we are. What is partial f with respect to z? We were given that. It's x plus y. So coming back down here, partial f, partial z is equal to x plus y. So I have x plus y equals x plus y plus partial h, partial z. Eliminating both of those, we have that 0 equals partial h, partial z. And if the derivative is 0, that must mean then that h of z is going to equal some constant. And I do not need to write this as a function of a variable because we already dealt with all three of our variables, x, y, and z. So in this problem, my function x, y, z is equal to xy plus xz plus zy plus c. And that's my final answer. So that's how I can find the potential function of a conservative vector field with 3 variables, x, y, and z.